Okay, in the last lecture we had seen basically the path generation with three precision points, how to go about the design task. We had P1, P2, P3, and then we used the concept of inversion to basically come up with the path, designing a coupler point to move through three selected points, three precision points. Now we look at something called path generation with timing. So we will see what we mean by that. So as what we are going to do is we are going to start with three precision points as before. So here I have P1, P2, P3, which is supposedly on a straight line. Now we are going to specify that when we assume, let's say that the crank angle position here is 180 degrees or whatever, depending on if I measure angle from here, it is 180 degrees. Now we say that to go from P1 to P2, it should do that in 35 degrees of crank this link rotation, input link rotation, and similarly it should go from P2 to P3 in 70 degrees of rotation. This is just, of course, arbitrary numbers that I have thrown at you, but fundamentally we are saying that we are going to time the rotation. So to go from position 1 to position 2 is 35 degrees of rotation of the link. O2A, and to go from P2 to P3, the link O2A will rotate by another 35 degrees to take you there. So this is what is demanded. So this is called path generation with timing. So okay, so now what we do is first thing that we do is we join O2 with P1, P2 and P3. So these lines are drawn as shown here: O2 P1, O2 P2 and O2 P3. These are the three crank positions, the green ones that we have drawn. The next step to this, after having drawn this O2 P1, P2, P3, is to reflect, basically rotate O2 P2. So we assume that O2 A1 is fixed, that is we are fixing in that same position as before. At we don't know what is O2 A1 length, we have not chosen that, unlike the first case. All that we know is that the O2 A1, O2 A2 are at an angle of 35 degrees, and similarly O2 A2 to O2 A3 line is basically at an angle of another 35 degrees. So we only know that, we don't know where A1 is on that O2A line. So we are trying to find that out. We assume that we have fixed this at O2A1, so that means the input crank is basically fixed. In the earlier case, if you remember, we started off by saying that the coupler is fixed at that A1 P1 position, but here we start by saying that the crank is fixed. So in the inversion, we can locate basically P2 prime by rotating O2 P2 essentially anti-clockwise about O2 by 35 degrees. So you can see that I take this line. So I have this line O2 P2, I rotate it by 30 degrees and I get O2 P2 prime. And similarly, because what happens is that if I were to look at sitting at O2A1, P2 prime will now move towards me. And similarly, I take P3 prime and rotate O2 P3 by 70 degrees, which is what we have. So this is the O2 P3 line and this is the O2 P2 line. So of course, these distances I have kept the same while plotting that, right? So that means O2 P2 is equal to O2 P2 prime, but is 35 degrees to this side. Similarly, O2 P3 is the same length as O2 P3 prime, but it's moved by 70 degrees. All right. So now we now try to locate basically A1, which is the crank location. So to do that, what we do is we join P1 to P2 dash as well as to P3 dash, and we are going to draw the perpendicular bisectors from P1 P2 dash and P1 P3 dash in this inversion. The intersection is at A1. So therefore we have now located the first crank position O2 A1. Remember, O2 A2 is 35 degrees rotation from O2 A1 in the counterclockwise, in the clockwise direction, and O2 A2 rotated by another 35 degrees will take me to O2 A3, which is in the other direction. Now, in order to find the other floating pivot, we basically follow the process that I had outlined in the previous lecture. So here we initially locate where A1 is going to be. Earlier we had chosen A1 arbitrarily, and then we started off the design. Here we are going to demand timing, which means from 1 to 2 the crank rotates by a certain amount, 2 to 3 it rotates by a certain amount, which is what we mean by timing. And therefore once we locate that A1, we follow the same process that I had outlined in the previous lecture, and we will get basically the path generation done for P1, P2, P3. So I have done that, and here's a slightly better version of the path following, the path generation. So here we can see the video. Let me open that fully. So you can see P1 to P2 to P3. It's not too bad, unlike the previous case with this 35-degree timing. P1 to P2 is almost like a straight line. P2 to P3 also is almost there, but with a small twist there. You'll notice that this is not quite a crank, this is not quite a Grashof mechanism, because you can see the coupler curve is essentially open. So you can see P1, P2, P3, and then of course it stops there. We don't have anything further than that. All right. So therefore, so that kind of ends the path generation. So we have done basically 3 precision points. Just to summarize before we move on to rigid body guidance, we have done the coupler a point on the coupler moving through 3 prescribed what are called as precision points, P1, P2, P3. And we did the first case that we did was a general case where we chose the O2, O4, the fixed pivots. We also chose the crank length and the initial crank position at 1. And then from there worked out what should be the other floating pivot, where should the other floating pivot be located. So we went through the construction and came up with where the floating pivot should be located. Now, we also looked at the case of a path generation with timing. So now let's move to a problem where instead of points, we now look at the path generation, of course, involves a point on the coupler. Now we look at what is called as a rigid body guidance problem, where we design using 3 positions of a line on the coupler. So this means not only the individual point has to pass through these things, but the line orientation is also important. So now we have rotation or orientation as an important. So let's go back to the car boot example, the Tigor boot that I have. I have frozen this at the 3 positions that I'm going to use for the design. You can see I have stuck a piece of paper and I have drawn a red line here. So this is one of the positions of a line on the coupler. So this what do you call the car boot lid is basically a part of the coupler. So this is another intermediate position too. And finally in the closed position, this is where it is going to be, right? So I'm basically interested in designing a mechanism which will move this line which is part of the coupler body through these 3 positions. So that's basically the goal of the exercise. So I have uh, very carefully extracted the coordinates, and I have given you the orientations here. A1, B1, A and B are 2 points on that whatever piece of paper that I have stuck. These are not what do you call the floating pivots, can be, but in this particular case they simply are 2 points defining the line A1, B1. A2, B2 is the intermediate position, and A3, B3 is the closed position, which is at that angle. So you can kind of feel that, you know, this is a fully open and this is the closed position and this is an intermediate position. So our idea is basically to have a mechanism which will guide us from A1, B1 through A2, B2 to finally A3, B3. And these have been carefully extracted from the photos that I showed you. So remember the photos. So this is that, and over here the intermediate A2, B2, and of course A3, B3. So this is these have been extracted by looking at the coordinates on the photograph, and I have ensured that the photograph itself is taken from a camera which is basically attached to a tripod, so that the different sequences, the coordinates remain the same. All right. Okay. So now the first step approach we are going to do is the usual approach where we are going to say, look, let me select the fixed pivot locations for this 4 bar. Remember A1, B1, A2, B2, A3, B3 are all part of the coupler, which is what the boot lid is. So we are going to select the positions. Now I'm done a little bit cheating. I said, okay, all right, I have seen my car and I have approximately gone ahead and measured. So what I did is I see, look, I know where it is. This is one pivot and this is the other pivot. So you can see this hidden behind this, but basically it is located just behind this and just behind this. So I've used that information essentially to what did I do? Yeah, I basically used the information to come up with the fixed pivot locations. So these two have been obtained from the photos. So I have located these. So my O2 and O4 are fixed on the car body. So now with this, I'm going to try to come up with a four bar mechanism which will take me through the three positions, the coupler through those three positions. All right. So what do we do? First thing that we do, of course, is once again, basically going into the kind of a mode of inversion. So what we say is, look, I'm going to assume that the coupler is basically frozen at A1, B1. So that means imagine my lid is remaining the same, but imagine the car is rotating, which is a little difficult to believe, but that is the kind of imagination that you have to do. The real car doesn't rotate, but for the sake of construction, we can do this. Now, Dr. Abhijit had mentioned a little while ago something about using a tracing paper. So this is a design process where a tracing paper is very helpful. So what we are basically going to do is we are going to now first what we draw is, you can see here there is a green triangle that I have constructed. So I'm going to say, look, from A2, I'm going to connect O2, and similarly from B2, I'm going to draw a line to O2. So now we have this little triangle. So we basically now, if you have a tracing paper, you can draw this. Then basically you take the tracing paper and then rotate it so that A2, B2 now coincides with A1, B1. If it does, what you will find is that since I have to rotate A2, B2 to come and line up with A1, B1, O2 would have moved to this position. So when you do this, so you imagine you have done this, you have all these three lines on a tracing paper, and then you have drawn this little triangle with the original position O2 and O4. O2 and O4, let's say, are at the bottom of the tracing paper. The triangle is at the three lines are at the top of the tracing paper, and I have O2, O4 on the sheet below that. Now, when I do this, what happens is that when I rotate this and then line it up with A1, B1, essentially O2 will move to O22, which is in the inversion. Basically, since the coupler is remaining fixed, when I go to A2, B2, actually it will appear that O2 has rotated in the other direction. So if I just simply line up the green triangle with the gray triangle, I will get O22. So A1, B1 to A2, B2 to get O22. So we follow the same practice with look at what does so now instead of joining to O2, suppose I draw the lines from A2 and B2 to O4, so which is what is shown here, this green triangle. Then we do the same visualization exercise. So I now rotate this triangle such that A2 goes to A1 and B2 comes to B1. Then that gray triangle is what I will get, and O42 is the location that I will have in the inversion. So, so we have both O22 and O42 in the inversion. So we repeat this exercise. So we do this now. You can see if I repeat this exercise with A3, B3, now I join to O2 the lines from A3 and then rotate it such that, so I take this and then make A3 coincide with A1 and B3 coincide with B1. So this whole triangle swivels like that. You can see O23 has the O2 has now swung to this position. So as I said, this is best if you can get a tracing paper. Please try this exercise using a tracing paper. It works beautifully. So you draw all these triangles, and then if you rotate, you will be able to see what I'm basically saying. So we are simply taking these various positions, A3, B3, A2, B2 lines, and then swinging them to coincide with A1, B1, and then looking at where the fixed pivots will basically go. So I have, you can see I have O22 here. Now O23 goes over there. Of course, this is O21, right? We do the same exercise now with the other fixed pivot. Now from A3 and B3, we now draw lines to, so this we have done already. Okay, the next step is basically to do the same for O4. So A3, B3, I connect to O4, and we do the same exercise. A3, this will swing to A1, and B3 will swing to B1. When I do that, it turns out O43 comes out to be somewhere here. Okay, which is effectively very close to the A1 position that you have there. All right, that's just because of the dimensions that we have chosen. All right, so we now have for the three prescribed positions. So remember that the coupler has been fixed at A1, B1. So we said, well, what happens if so A2, B2 and A3, B3 were made to coincide with A1, B1. In the inversion, we had O22, O23, which are the two positions of the fixed pivot in the inversion, which rotates. Similarly, O4 rotates to O42 and O43. All right. Now we do the usual thing. We join O21, which is O2, and O22, and similarly O22 and O23. We draw the perpendicular bisectors of these two lines. So you can see here, this is O2, O22, this is O22, O23. The perpendicular bisectors are drawn. The intersection basically is what I'm calling as I. We do the same exercise for O4, O42 and O42 to O43. That intersects, where does that intersect? No, I have not shown it on this picture. I'm kind of staring at that. So the first thing is basically I gives me basically the first floating pivot. So this intersection of these two gives me A or I, which is one of the floating pivots. Similar construction for O4, O42, O42, O43 gives me K, which is basically the other floating pivot. So we have now got I and K are the floating pivots on the coupler. And here is the design that you come up with. So you can see this design, K and I are pretty close to each other. So if you now finally look at the construction that you have, I have O2, K is, and K and I are basically on the coupler, and O4 is out here. So in this position, in this configuration, this is at first position, fully open position, as you can see. I have shown you on the right hand side the actual mechanism. So you can see that this is O2I. Remember, actually O2I is my this link, and O4K is basically this link. So you can see that the two joints that are there, the one pivot is out here, that is I, and this is K. So you can clearly see that I have not done a bad job of coming up with a mechanism design which will basically mirror the opening of my boot. So not a bad job. We can see that the basic shape is pretty similar. The design that we have come up with, the mechanism 4-bar that we have come up with, will work like this in this particular case. All right. So let's see, animate this, and here is what I have. Make it full screen. You can see that it's now closing. So you can see that this is horizontal, and then the final position is somewhat of a slightly angled position. So that's the last one. Let me play again. You can see that this is where we start from, and then E and D kind of move away. So fully open, and then we are going through. Somewhere there is the intermediate position, and then we are going down all the way down. So So now I've designed a 4-bar mechanism. So this is how the Tata Motors guys would have designed this, and just we just decided to mimic that and see how good we can be. We have not done a bad job, of course, of reverse engineering. So people talk about reverse engineering, and this is one of the reverse engineering examples where I come up with this mechanism by simply looking at this, and then I can come up with the dimensions. Of course, I can measure. You will say, well, what's the big deal? I can measure, but I have the methodology by which I can design this particular mechanism. Very good. So this is a design where we designed a path guidance basically with sorry, motion guidance. We did path guidance, a little bit of path guidance with timing. Then we looked at basically motion guidance where we fixed the we chose the fixed pivots. I will stop at this point in this lecture. The next lecture, we are going to wind up with the first part of the kinematics part of it with the next lecture, which will we will do one more type of design with rigid body guidance, where instead of choosing the fixed pivots, we will choose the floating pivots, which means that in this particular case the E and D will be chosen. So if you go here, I will choose ED and then find out where AB should be, right? So we will do a design in that fashion, although that is not a very preferred method of design, as I keep repeatedly saying, because you can't have a fixed pivot at an arbitrary location. It has to be on the body somewhere where it is convenient, like what we have done for the car body here. And on the boot lid, I can have it wherever I want the coupler joints. So, but we will look at that, and then I will introduce you very briefly to the coupler curve idea, and the various types of shapes that the coupler curve has, and what is called as the coupler curve atlas. I'm not going to get very deep into this. I'm just going to talk in a very general sense, because we don't have analytical equations for the coupler curves that we derive. We're just going to show various possible shapes, and by looking at some of these coupler curves, we get ideas of path generation, good path generation mechanisms from there. All right, so I will stop here, and this will be the end of